Hello everyone, this is lecture 17 of ComSci 141, P versus NP. In the previous video, we talked about undecidability and intractability. If you recall, undecidability was all about the limits of computation for a computer. So it talks about what problems can a computer solve and not solve. Okay? And then for intractability, we assume that a computer problem is solvable already. And the problem now is whether the algorithm for it runs in reasonable amount of time or polynomial time, or does it run in at least exponential time, which is unacceptable. So it's only solvable in theory but not in practice. Okay, so takes too long in practice, then we call that intractable problems. Okay, so currently we are now in our last topic for ComSci 141, which is about P versus NP. So in today's video, we will talk about the distinction between P problems and NP problems, and then we'll also talk about NP complete problems and how to cope with NP completeness. Okay, so let's start. So recall from last video that we talked about the tale of three friends. So we talked about Alice's problem, Alice, who works in telecommunications, had the vertex cover problem, right? Bob, who worked in biotechnology, had the click problem, and Carol, who works in finance, had the independent set problem. So let's review these three problems quickly. So in the vertex cover, which was Alice's problem, you were asked or you were given a network of telecommunication centers, right? So the nodes here, or the vertices in the graph, are the telecommunication centers, and they are linked together by cables, so forming a network. And then they wanted to install a set of monitoring devices in the telecommunication centers so that they can check the integrity of the network. So they wanted to find the minimum number of centers that they could install the monitoring devices into, such that the whole network is covered. And if you recall, the minimum number of devices that we could use to cover the whole network is 4, and that is if we install it in C, E, G, and H, right? So in here, if it's C, E, G, and H, then we will have it here, 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 and here. And these 4 monitoring devices will monitor this line, this line, this line, and this line from C. And then from E, it can monitor E to F and E to H. From G, it can monitor G to D, G to H, and G to I. And then finally from H, it can also monitor this one. Okay, so yeah, C, E, G, and H. So yeah, okay, so that was the problem of Alice, right? Next, we had the click example for Bob, and the problem here was that the nodes this time are genes, and if the genes are linked together by an edge, that means that they can work together. Okay, and Bob's problem was to find the largest group of vertices such that all of them were connected to each other. So we call that a click. So from last time, we said that the biggest cluster size here is 4, and that would be B, C, E, G. Okay, because here B, C, E, and G are all connected to each other, right? So B is connected to E, connected to C, and to G. C is connected to G, and to E, and to B as well, and then you have that. So you have this like connections, so all of them are connected to each other. Okay, so that is the click problem. And then for Carol, who works in finance, she had the independent set problem. So given these things that they could invest into, they don't want to invest in two things that are more or less similar, right? Because if one of them fails, then the other one will also be affected. So they don't want to put all their eggs in one basket. So they wanted to diversify, but they also wanted to invest in as many things as possible. So the answer here for the independent set problem was they could invest in a maximum of 3 investments. So that would be for industrial manufacturing, the bank, and for silver. So if you invest here, here, and here, then all of them are not connected to each other, right? So if you added one more, then it would be connected to one of these 3 things. So that is the maximum that you can invest in following those constraints. Okay, so those were the problems of the 3 friends. So usually in these types of problems, there is 2 versions of the one problem. So you have the optimization version and the decision version. So what's the difference between the two? So in the optimization problem, you're trying to find the best solution. Okay, so meaning you're trying to find the smallest vertex cover, or the largest click, or the largest independent set. Okay, so it's either the minimum or the maximum depending on the problem. In the decision problem, you're only asking, is there a solution of size k? Okay, you're not looking for the best solution. You're just wondering if is it possible to do this with only, let's say, 5 vertices or 3 vertices. Okay, so a solution of size k. So is there a vertex cover solution using only 5 vertices, and so on. Okay, so decision problem is somewhat easier than optimization, because in optimization you have to find the best solution. Okay, now how are these two related in terms of tractability? So if the decision problem is tractable, that means that it has a polynomial time algorithm, right? Because tractable problems are assured to have polynomial time algorithms in a deterministic computer. So if you have a solution that runs in polynomial time, then you can use that solution, that polynomial time algorithm, repeatedly to solve for the optimization version. Okay, so that means that the optimization version will also be tractable. So how will you do that? So for example, if you only have, like, let's say, if you have a algorithm for the decision, you have a decision algorithm that takes in k as an input, okay, and then either yes or no. So meaning, does a solution using only k vertices exist or not? Okay, so this is the vertex cover decision algorithm. So if you wanted to use this algorithm to find the optimal version, you can start with n over 2. So let's say that you have 8 vertices. Let's say n is equal to 8. Let's start with 4. Can you do it with 4? Okay, so start at the half, and then if you find the solution, then you'll try to decrease it because you're looking for the minimum, right? So since you're looking for the minimum, we know that solution of size 4 exists. So let's try k is equal to 3. Then let's feed that here again. If it exists, then you reduce it to 2 again. If it does not exist anymore, then that means that k is equal to 3 is the smallest possible. Okay, so you'll find the smallest possible by continually decreasing. But what if in k is equal to 4, it's wrong, meaning it does not exist? So what you do is you raise the value of k instead. So you'll try k is equal to 5. Does that exist? If it's not, then you raise it to k is equal to 6. If this one is okay, then you've found the minimum. Okay, so starting at the middle makes it faster for you to finish, because you already eliminate half. So if k is equal to 4 is successful, then you don't need to check the upper half because you're looking for the minimum, right? So you're only going to go down from there. Now if k is equal to 4 is not successful, then there is no point in checking the lower half also, because even in k is equal to 4, it's not possible. So what more with lesser number of vertices, right? So you can only have you only need to check the ones in the upper half for you to be able to find the answer. But this is the process of how you can use the decision algorithms repeatedly to find the optimum answer. Okay, so the optimization version, you can also find the solution for it. Okay, so yeah, so that is how they are related. So if so let's try to answer this exercise. If the optimization version is tractable, does that mean that the decision version is also tractable? Well, yes, because as we said, optimization version is already harder. So if you have a polynomial time algorithm for the optimization version, that means that there should also be a even simpler algorithm for the decision version. Now, how about if the decision version is tractable? Does that mean that optimization is automatically tractable as well? Well, yes, we already mentioned this. You can repeatedly use the algorithm for decision to find the optimal answer. Okay, and then how about if optimization is intractable? What does that mean for decision? Is it also automatically intractable, or is there a possibility that it's still tractable? Well, unfortunately, it's intractable already. Okay, so if optimization is intractable, that means that decision version is also intractable. And of course, if the decision is intractable, the even harder optimization version will also be intractable. And the reason for this is because statement 2 is actually a contrapositive of statement 3. So if dec is tractable, implies that opt is tractable. The contrapositive statement is a equivalent statement, which is if not if optimization version is intractable, implies that decision is also intractable. Okay, so remember contrapositive. If A is equal to B, the contrapositive is if not B, then not A, and these two are equivalent statements. So you have decision is tractable, so this is A, and then optimization is tractable, so this is B. This one is not B because optimization is intractable here, so that is the opposite of B, and then this one is not A since decision is tractable here, and then it becomes intractable. So number 2 and number 3 are actually contrapositive statements, so they have the same truth values. Okay, so that's it. So regardless of whether you're using the optimization or the decision version, if a problem is tractable, then both are tractable. If it's intractable, then both are also intractable. Okay, so yeah. Now let's see some problems that are tractable, or problems with polynomial time algorithm. So those problems are sorting. So the sorting problem is tractable because it has polynomial time algorithms like quicksort, merge sort, and other sorting algorithms. You also have searching because you have the binary search, sequential search, jump search, and so on. You also have problems like longest common subsequence, minimum edit distance, which, if you recall from your algorithms class, uses a dynamic programming to solve it in polynomial time, right? O of n squared, yeah, and then, or O of mn, both are polynomial. You also have minimum spanning trees, which has the Prim's and Kruskal's algorithm. You have shortest paths, which has polynomial time algorithms like Dijkstra's, Bellman-Ford, Floyd-Warshall, and Johnson's algorithm. So all of these problems are tractable because they have polynomial time algorithms that exist to solve them. Okay. Now, how about problems with no known polynomial time algorithm yet? So we're calling them intractable with a question mark because it's still undecided for now, right? Because so far, we don't know if there is a polynomial time algorithm that exists. It could be that it really does not exist, or it could also be that it just hasn't been discovered yet. So we're calling it intractable with a question mark. Okay, so what are some of these problems? So you have the vertex cover, click, and independent set, which are the problems of the three friends. Okay, so we're not yet sure if there is a polynomial time algorithm for them, okay, that will work for all possible instances or all possible inputs. Okay, because again, when we're talking about tractability and intractability, the polynomial time algorithm has to work in polynomial time for all possible inputs. Okay, there could be algorithms that work in polynomial time but only for special cases, so that's not counted. Okay, it has to be a general polynomial time algorithm. Okay, so now let's try to review the computational models that we have seen so far. And really, we have seen two types of computational models, right? The deterministic version and the non-deterministic version. So for deterministic computational models, we saw the deterministic finite automata, the DFA, and then the deterministic Turing machine, right? So remember that for deterministic models, in one state, in the current state, you can only transition to one state. Okay, so you are sure, or it's always clear what will happen next. Okay, there's no guessing, because from one state you are surely going to this next state according to the transition. Okay, and take note that our current computers are deterministic. Okay, there is no sense of randomness or sense of non-determinism in our current computers. Well, there is randomness, but even the randomness is just like fake, because if you know how random number generators work, it's just pseudo random, right? But anyway, I'm going off topic, but yeah, that's deterministic computational models. Okay, it's always clear what will happen next from one state to another. Now, on the other hand, we also had non-deterministic models like the NFA, the PDA, the pushdown automata, and non-deterministic Turing machines. Okay, and the idea for non-deterministic models was that from one state you can transition to one of multiple choices. Okay, so you had a choice of where to go, and non-deterministic models also had this power that it can always correctly guess the choice that will lead to the optimal answer. So if you wanted to like accept the string, then it can guess correctly which of these branches to follow in order to reach like a final state or an empty stack, or to be accepted basically. Okay, so it can always correctly guess the choice that will lead to an optimal answer. And this is very helpful in solving difficult problems, because by always correctly guessing the choice, then you can answer the problem quickly, right? The problem is there are no non-deterministic computers currently. Okay, so all of our computers are currently just deterministic computers. So no like magic computer that will correctly guess the choice. Okay, so no non-deterministic computers yet. There could be one in the future, who knows, but right now there's none. Okay, now let's imagine what if that non-deterministic computer really did exist. Okay, what would be the result of that? So if a non-deterministic computer existed, we can solve problems like the vertex cover, click, and independent set in polynomial time. And why is that? Because remember that it has the power of guessing correctly, right? So for each vertex in these three problems, the non-deterministic computer will just guess correctly whether it is part of the solution or not. So for example, for vertex cover, vertex A, will I include this in the solution? Then it will just guess correctly, right? Because it's non-deterministic. So I can see into the future, and I have seen that A is part of the solution, but B is not. So it can just guess correctly each time, right? So you can finish the solution in polynomial time because it will just guess correctly. Unfortunately, the bad news is, of course, non-deterministic computers don't exist yet. But can we try to simulate non-determinism using deterministic computers? Because so far, we have shown that in our non-deterministic models, we could simulate it in deterministic computers, right? For us to be able to implement them. But if we simulate non-determinism using a deterministic computer, what would happen is you would have to go through all possibilities. So you have to brute force it to guess the correct answer. So go through everything to search for the minimum solution or the maximum solution, depending on the problem. But if the number of possibilities is exponential, so O of 2 raised to n, then the running time of your brute force algorithm will also be at least O of 2 raised to n, which is exponential. And this is the bad news, okay? Because if you simulate it, you will have a lot of possibilities, so exponential number of solutions. So going through all of them will take at least exponential time as well, okay? So there's two things. If the non-deterministic computers exist, then the three problems that we mentioned can be solved on a non-deterministic computer in polynomial time because it can just guess correctly. But if the non-deterministic computers cannot exist, then the non-determinism can only be simulated using deterministic computers, and we will be able to do that in exponential time because there is an exponential number of possible solutions. Okay, so these are the two possibilities. If non-deterministic computers exist, it can run in polynomial time, but if it cannot exist, then we can only simulate it and it will take exponential time. Okay, so yeah, if non-deterministic computers existed, it can be solved in polynomial time. So this naturally transitions us to the two classes of problems, P versus NP. Okay, so now that we understand the difference between running in polynomial time if a non-deterministic computer existed, and running in exponential time if the non-deterministic computer did not exist, because it's exponential time because we only simulated it on a deterministic computer. So this is now a good time to introduce the P versus NP classes. For the class P, this is the set of problems with a polynomial time algorithm on a deterministic computer. So these were the problems earlier that we mentioned, like the sorting, the searching, the minimum edit distance, the minimum spanning trees, and so on, shortest paths. Okay, so these problems have polynomial time algorithms that can be solved on a deterministic computer or our current computers right now. Okay, so the P here stands for polynomial time. Now the class NP are problems with a polynomial time algorithm on a non-deterministic computer. Okay, so it will have a polynomial time algorithm if a non-deterministic computer existed. So the NP here stands for non-deterministic polynomial. Okay, so non-deterministic polynomial. So if you try to imagine it in a grid, so deterministic computers, polynomial time, that is class P, and then deterministic that takes exponential time, that is NP. But if it's non-deterministic computers in polynomial time, that is NP. Okay, so that is the difference between P versus NP. So they both run in polynomial time, but P runs in polynomial time in a deterministic computer, while NP runs in polynomial time in a non-deterministic computer, if it existed. Okay, so actually the real diagram for P and NP is something like this. Okay, P is inside NP. So if a problem has a deterministic polynomial time algorithm, then it also has a non-deterministic polynomial time algorithm, right? Because if you remember from our earlier equivalence, like from DFA to NFA, like we just had, if it's one state, then we can just convert it into this, right? So if you remember this one, so our conversion from a deterministic to non-deterministic is easy, because if you have one transition in DFA, then the choice of transitions for NFA is easy. You just have that that one also. Okay, so if a problem is deterministic, then it's also automatically non-deterministic. Okay, the problem is, if the problem has a non-deterministic PTA, okay, so if it's in NP, we're not sure if it also has a deterministic PTA. Okay, so that is the current problem of P versus NP. Okay, so again, P problems are those that have a polynomial time algorithm on deterministic computers, like sorting, searching, and so on. So we already mentioned this earlier. Okay, while NP problems are those with non-deterministic polynomial time algorithms on non-deterministic computers, like the vertex cover, click, and independent set. Okay, so formally, an NP problem is defined as follows. So a problem is non-deterministic polynomial if, first, the solution length is polynomial in input size n. So the length of the solution is a factor of n in polynomial power. And the possible solutions can be verified in polynomial time. So the time that it takes for you to verify that it really is a correct solution is also in polynomial time. Okay, it doesn't take long, so it's just a quick verification. So vertex cover, click, and independent set are NP because they're given an input, as an input, a graph with n vertices, and the solution is O of n, right? Because in the vertex cover, you're looking for the minimum amount of vertices, so that's less than n. For click, the biggest amount of the largest amount of, or the largest number of vertices, and then independent set also is largest number of vertices. Here it's all connected, here it's none of them are connected. So those can range from 1 up to n. So those are all in O of n, okay, the solution. And we can also verify it in polynomial time, O of n squared, because in vertex cover, we just have to check all edges if they are all covered by the vertices, right? In click, we have to check that the edges of the given solution are all connected to each other. Okay, so, and then for independent set, same thing. We have to check that none of the vertices are connected to each other, so that could entail checking all edges as well. So we could verify the solution in polynomial time. So those these three are valid NP problems. Okay, and recall also that these three are reducible to each other, right? So vertex cover can have the or click and independent set had a relation in which click's answer can be independent set's answer on the inverse graph, and then for vertex cover and independent set, you do it the solution is the opposite. So whatever is in the independent set is the answer for vertex cover if you remove everything. Okay, so if you have B, D, E, and F as the answer, you could have A, B, C as the opposite. Okay, so something like that. So they are all reducible to each other, as we saw in the previous video. So let's talk a little more about reduction of problems. So how do you reduce one problem to another? So in reduction, you have a polynomial time algorithm that transforms the input of problem X into the input of problem Y. So you kind of transform it from problem X into problem Y, so that problem Y can solve the problem X. Okay, so solving Y on the transformed input means that you're also solving X on the original input. Okay, just like what we did with the independent set and the click, right? We converted the click clicks graph into the inverse graph, and then that's when we solve the independent set, right? Now, yeah, as I mentioned, and then so let's answer this one. If problem X is reduced to problem Y, which problem is harder? Is X harder or is Y harder? So try to think about that one first. Which one do you think is harder? Problem X or problem Y? Well, if you can reduce problem X to problem Y, the harder problem is problem Y. That is because your problem X is basically piggybacking on problem Y, right? So it's like you're asking a friend, "Hey, are you going to the store? Then can you please buy me some of this?" So you're asking your friend to do your job for you. So that means that your friend must have more things to do, and then on top of it, he's also doing you a favor. So in that case, problem Y is doing more, right? Because on top of it, he's also solving your problem for you. Okay? Now, if problem X was harder, then problem X should be the one that is doing it, not problem Y, right? Like if you have more things to do, don't ask your friend to do it for you. Your friend has to be the one to ask you for the favor, right? Does that make sense? Yeah. Anyway, we're going off topic. So, if X is reducible to Y, then solving Y requires at least as much effort as solving X. Okay? So, Y is harder. So, now, let's talk about these problems that are called NP-complete. So, a problem X is NP-complete if, number one, it has to be in NP. Okay, so problem X is non-deterministic polynomial. So it has a polynomial solution length and polynomial time in verification. And number two, every NP problem reduces to problem X. Okay, so every problem in NP can be reduced to problem X, meaning problem X, the NP complete problem is really very hard because all NP problems can be reduced to it, right? So imagine all of these NP problems like vertex cover, click, independent set. If they can be reduced to the NP complete problem, then solving this NP complete problem will also solve these other NP problems because they're piggybacking on NP complete problem, right? Because remember, we said that if X can be reduced to Y, then Y is harder, right? So if all the NP problems can be reduced to the NP complete problem, so NP can be reduced to this and another NP, this one is the hardest NP problem of all, right? Because it can solve all NP problems by solving its own problem. So all NP problems can piggyback on the NP complete problem solution. Okay, so NP complete is the hardest in NP, and being NP complete is a strong evidence of intractability, but it's not automatic as well. It's still an open question for now. Okay, now besides NP completeness, there is also this thing called NP hard problems. And for NP hard problems, they are at least as hard as NP complete problems. So they are at least as hard. So meaning it could be as hard as NP complete or even harder. Okay? So, and take note that NP hard need not be in NP. Okay? They might even be outside the NP class. So they may not have a non-deterministic polynomial time algorithm that exists. Okay? So the whole complexity class hierarchy looks like this. Okay, so let me so you have the P class here, which is has a polynomial time algorithm in deterministic computers. Okay, this one has a polynomial time algorithm in non-deterministic computers, the NP. Now, the set of classes here, NP-complete, the ones in green, are the hardest NP problems, because all the NP problems can be reduced to the NP-complete problem. So this is the hardest, right? And then NP hard is at least as hard as NP complete. Okay, so some of the NP hard are also part of NP complete, and then some of NP hard are outside NP. So it's not even NP. Okay, so which one of them is the hardest? It's of course the NP hard, because it's at least as hard as the hardest NP question. So it's even, some of them are even harder. Okay, so now let's go back to the problem of P versus NP. So we illustrated P and NP as P being inside NP, but the question really is, are the two sets equal? Is P equal to NP, or is P not equal to NP, meaning they are two different sets altogether? Okay, so that is the open question right now. P is equal to NP, or P is not equal to NP? So what does this mean really, that they are equal or not equal? If P is equal to NP, that means that if a problem has a non-deterministic polynomial time algorithm, like your vertex cover, independent set, and click, does it also have a deterministic polynomial time algorithm? So does it have an algorithm that runs in polynomial time in a deterministic computer? Okay, so does VC, click, IS have a polynomial time algorithm in our current computers? That is still an open question. We still don't know right now. So still an open question, and it's one of the Millennium Prize problems. Okay, so the Clay Mathematics Institute will actually offer $1 million to those who can prove that either P is equal to NP or P is not equal to NP. Okay, so if you can prove that P is equal to NP or P is not equal to NP, one of them, then you have $1 million. Okay, so for those of you who wants to try, then you can try. But well, if it was easy, then someone would have solved it by now, right? But there's no it doesn't hurt to try. Anyway, so if P was equal to NP, that means that the set is just one whole set, right? So we illustrated P and NP as like P is inside NP. Now if P was equal to NP, then they will just be one set, right? It's not like a subset, it's just the same set. Okay, so all NP problems have a deterministic polynomial time algorithm. And what would that mean? Yeah, let's look at that later. If P is equal to NP, okay, then that means that they are totally different. Okay, if P is not equal to NP, then that means that all NP problems, including vertex cover, independent set, and click, will take at least exponential time to solve. So no polynomial time algorithms on a deterministic computer. Okay, if P is equal to NP. So that means that the problem of the three friends will take at least exponential time to solve, okay, in our current computers, if it is proven that P is not equal to NP. Okay, so we mentioned that NP stands for non-deterministic polynomial, right? So the common mistake is that people who are not familiar with P versus NP thinks that NP means not polynomial. Well, that's just not true, okay? Because it's not yet proven that NP is really not polynomial. It's still an open question, right? So the term NP was coined by Donald Knuth in 1974. And again, please don't make the mistake of thinking that NP is not polynomial, because it's not yet proven that it is really not polynomial. Okay, now another suggested name when they were coming up with this concept of non-deterministic polynomial problems was PET or PET, because it would have worked seamlessly if the problem is still open, like P versus NP is still an open question, then PET would mean that it's NP is possibly exponential time, because we still don't know, right? It's possible that it's exponential. Now, if we prove that P is not equal to NP, then it would be called provably exponential time, because we have proved that it really is not polynomial and it is in fact exponential time. And if it was proven that it was P is equal to NP, then we would just call it previously exponential time, because now we know that it's in polynomial time, so it's previously exponential. So PET would have worked also, but they stuck with NP, which is non-deterministic polynomial. Okay, so just a little background and history about the name. Now, how is NP completeness related to the P versus NP problem? So remember that the NP complete problem is the hardest NP problem, right? And if one NP complete problem is solvable in polynomial time, okay, imagine that we had an NP complete problem and we found a polynomial time algorithm in a deterministic computer. What would that mean? Well, that means that all NP complete problems are also solvable in polynomial time, right? Because we could just reduce these NP complete problems into that one problem. And this will prove that P is equal to NP. Because remember that all NP problems, okay, if this is an NP complete problem, remember that all NP problems can be reduced to it, right? And reduction again means that by solving this problem here, NP complete, we can also solve the other problem. So if x is it's reduced to y, if you solve y with a polynomial time algorithm, then x can also be solved in polynomial time. Okay, and let's add more, like the VC, IS, and click. So if you find a polynomial time algorithm in a deterministic computer, PTA, that is deterministic, and this is solved, then this means that this, and all NP problems can be solved in polynomial time as well in a deterministic computer. Okay, and that means that P is equal to NP, because now all NP problems can be solved in polynomial time. Okay, but if one NP complete problem is also proven to be solvable in at least exponential time, so it's the opposite naman. Okay, we've proven that this NP complete problem, no matter how clever the algorithm, can only run in at least exponential time, then all NP complete problems will also be solvable in at least exponential time, and this will also prove that P is not equal to NP. So it's all or nothing. If one NP complete problem is has a polynomial time algorithm, then all NP problems is polynomial time. That's P is equal to NP. But if one NP complete problem is also shown to have exponential time algorithm or can only run in at least exponential time, no matter how clever the algorithm is, then everything is also exponential time. So that means that P is not equal to NP. Okay, so that is the that is how important NP complete problems are, because they will decide whether P is equal to NP or not. Okay, because just proving one of them to have a polynomial time algorithm or running in at least exponential time will solve everything. Okay, now why are we interested in the P versus NP problem? What are the implications of having this problem? Now, if it was proven that P is not equal to NP, then problems like the vertex cover, click, and independent set will have at least exponential running time. So this is bad news for the three friends, Alice, Bob, and Carol, because that means that there is no polynomial time algorithm for their problems. Okay? So NP problems will be intractable. They cannot be run in a reasonable amount of time. It will be at least exponential. However, if the opposite was proven to be true, if P is equal to NP, then it would just be easy to solve the hard problems like the VC, click, and IS, right? But the downside is, well, this is good news for Alice, Bob, and Carol because it's their problems are solved, and that means that NP problems will also be tractable. But the downside is modern e-commerce would fall apart. Okay, why is that? Because modern e-commerce are transactions online that involve money, relies on cryptography, right? That the connection is secured, right? So the data that we send is encrypted, so that we don't have like man-in-the-middle attacks, or we don't have people who are snooping our network packets and intercepting them and being able to change whatever data is being sent, or like they can view information that is supposed to be private, right? So encryption solves that for us, right? So if we encrypt the data that's being sent, then only the sender and the receiver can be able to view the data in theory. But cryptography, most cryptography algorithms rely on how hard it is to factor two numbers. So later on, if you have if you get into cryptography, you'll learn about the public key and private key, and those two numbers are being multiplied together, and then that is the key that is being given, and only the sender and the receiver knows these two keys. So if the man in the middle attacks it, they don't know what the two keys are, so it's really hard to factor out the two numbers. But if P is equal to NP, it would make factoring two numbers really easy. Okay, because if you have like non-deterministic polynomial time, then you can just guess the two numbers right away. Okay, so yeah, it would make the modern e-commerce fall apart, because then none of our cryptography algorithms would work. Okay, everything could be intercepted and modified. So that is the downside. Okay, if we could prove that P is equal to NP, then the hard problems that make it hard for attackers to well do bad things will just become easy now. Okay, so yeah, it's the implication. So where is the computer science community on which side are they on? So some people are arguing that P is equal to NP. Some people are arguing that P is not equal to NP. So some of these people are Jack Edmonds. He conjectured that no PTA exists for traveling salesman. So he claims that P is not equal to NP, but this is only a conjecture. Okay, and traveling salesman is one of the NP complete problems. Okay, Kurt Gödel conjectured that P is equal to NP, and in general, most people believe it's widely conjectured that P is not equal to NP, but there is no formal proof yet, so it's still undecided. It's still an open question. Okay, so to give you a background on the sides of P versus NP, there are more than 60 attempts to prove that P is equal to NP. Then there are more than 50 attempts to prove that it's not equal to NP. And there was one proof for P is not equal to NP that was 102 pages long, but the proof fell apart because there was one error in page 67, and then everything was just invalid. So can you imagine the amount of work that they had to do to be able to come up with a 102-page proof only for it to fall apart because you had one error in one page. So it's really hard. Okay, so it's hard on both sides. So that's why it's still an ongoing question, and that's why it has a $1 million prize. Okay, so if you were interested in trying to prove one of the sides, like P is equal to NP or P is not equal to NP, how do you settle it? So how do you show that one side is valid or how the other side is valid? So if you wanted to show that P is equal to NP, then you only need to come up with a polynomial time algorithm for any NP-complete problem that works for all inputs. Okay? So you need to show just one polynomial time algorithm for any NP-complete problem, and you can already show that P is equal to NP, because by solving one NP-complete problem, which is the hardest NP problem, in polynomial time, that means that all NP problems can now be solved in polynomial time, right? For the opposite side, if you want to prove that P is not equal to NP, then you need to show mathematical proof that any algorithm for an NP-complete problem will run in at least exponential time. So in P is equal to NP, you only need to show one algorithm, right? But in P is not equal to NP, you need to prove mathematically that any algorithm for a NP-complete problem will run at least exponential time. So not just one algorithm or two algorithms, it has to cover all algorithms. Any possible algorithm, no matter how clever it is, has to run in at least exponential time. So this is a little bit more tedious, right? Because you have to prove it mathematically and for all algorithms. So okay, now if you're given a problem, how would you know if it's NP complete or not? Okay, how do you recognize NP completeness? Okay, or how do you prove that the problem is NP complete? So we just said that there is a set of languages or set of problems that are the hardest in NP called NP complete, because all NP problems can be reduced to it. But how do you actually say that it is actually NP complete? Okay, so to prove or to show that a problem is NP complete, first you need to prove mathematically that any NP problem, okay, can be reduced to that problem, to that NP complete problem, or you can reduce another NP complete problem to X. Okay, so you have two options. Either if you wanted to show that problem X is NP complete, NPC, you have to show that all NP problems reduce to it. Okay, show that all NP problems can be solved using this problem X. Okay, that's one. Or if you already have an NP complete problem, let's say Y, if Y, which is known to be NP complete already, if it can be reduced to X, okay, then that makes X NP complete as well, because if Y, which is already the hardest because it's NP complete, can be reduced to X, then X should be at least as hard as Y, making it also NP complete. Okay, so approach number 2 is easier to do, right? Because, well, you only need to prove it for one NP complete problem, right? But approach 1 had to be used when there was no proven NP complete problem yet. At the start, nothing was NP complete yet, right? So you can't use this method number 2 just yet. So you had to use this method number 1 to have like a seed NP complete problem. So you needed to have at least one NP complete problem to be able to use this method number 2. Okay, now fortunately for us, this has already been done. Okay, so you needed to prove mathematically that any NP problem can be reduced to this seed problem. So once the seed problem is proven to be NP complete, then we can use that problem to prove that other problems are NP complete. Okay, so once we have established at least one NP-complete problem, like this one, using this method, then we can use that problem to show that other problems are also NP-complete. So the good news is that Cook and Levin already did this about 40 years ago. They proved that the satisfiability problem is NP-complete. So this satisfiability problem turned out to be the seed NP-complete problem. And this satisfiability problem is being used to show that other problems are NP-complete as well. Okay? So what is the satisfiability problem? Also known as the Boolean satisfiability. You're given as an input a Boolean formula with n variables. And your output would be to set true or false values to the variables such that the formula evaluates to true. Okay? So assume that the formula length is polynomial in n. So let's give an example. So let's say that our Boolean formula is A or B and not C. Okay, so what would be the truth values of this for this statement to evaluate to true? If we tried false, false, false here, what would this evaluate to? False or false is false, and not false is true. So false and true is false. So this configuration is not it. Okay, what if we tried false, 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 true? If that's false, false, true, this is false or false. This becomes false, and not true, so that's false. False and false is false as well. So how about if we change this one? Make this false and then make this true. So false and false or true makes this. Okay, wait. Let me erase first. So this one is false. If it's FTF, false or true is true, and then not false is true. True and true is true, so this one is valid. So this is a solution, F, T, and F. But again, this is just a simple example. What if the length of the formula is like 100, or there are like 50 variables? So you had to, all possibilities would have to be 2 raised to n, because there are 2 possibilities for each variable. You have either true or false, right? So for these 3 variables, there are 8 possibilities. So you have the FFF, FFT, FTF, FTT, and then TFF, TFT, TTF, and then TTT. So the total number of possibilities is 8, and that is 2 raised to 3, because at each variable you have 2 choices, right? True or false, true or false, true or false. So you multiply that, that's 2 raised to 3 or 8. Okay? So that is the Boolean satisfiability problem. And they showed, Stephen Cook and Leonid Levin, in the Cook-Levin theorem, they showed that any problem in NP can be reduced to the satisfiability problem. Okay, and the idea in their proof is that they showed that any algorithm can be encoded as a Boolean formula, so you could answer it as a satisfiability problem. Okay, so the seed NP-complete problem was satisfiability, and they showed it to be NP-complete. Cook and Levin showed that it was NP-complete. So we'll use satisfiability to show that other problems are also NP-complete. So you could use the second approach now. Okay. So if we could reduce satisfiability to VC or satisfiability to click or to IS, then it was shown that vertex cover, click, and independent set were also NP-complete. Okay. So to show that a problem is NP-complete, first you need to show that it's in NP. So it has to have polynomial solution length and polynomial time verification, and find a polynomial time reduction from an existing NP-complete problem. And since we already have a seed NP-complete problem, this should not be a problem anymore. So some of the NP-complete problems that were already proven to be NP-complete are the satisfiability, click, vertex cover, independent set, graph coloring, Hamiltonian path, traveling salesman, partitioning, bin packing, set cover, knapsack, subset sum, scheduling, and timetabling. So these are just some of the NP-complete problems. There's more. There's a lot more. But if you are interested in these problems, you can look into them if you want to. Okay. So there's a library of NP-completeness. So starting with Richard Karp's 21 NP-complete problems. So this was the first set of early NP-complete problems that they proved to be NP-complete by using the satisfiability as the seed. And then there's also Gary and Johnson's computers and intractability, which also lists a lot of NP-complete problems. Okay. Now the bad news is that NP-complete problems are ubiquitous in the real world, and they're very important to solve. So going back here, we have problems like traveling salesman and partitioning, knapsack and scheduling and timetabling, like how to schedule the courses of a university such that the restrictions or constraints are being followed, like no conflict for the teacher, no conflict for the students, no conflict in the rooms. Okay, so they are ubiquitous, they're everywhere in the real world, and they're important to solve. So if currently they are intractable, meaning they don't run in polynomial time for now, because currently we only have the brute force algorithm that solves it for all types of input. Even if they're currently intractable, because we have to solve them, since they're important problems, we have to find ways to cope with NP-completeness. So if your current problem is NP-complete and P versus NP is still open, right, and we don't have non-deterministic computers yet, how do we cope with NP-completeness? Okay, so how do you solve a problem, an NP-complete problem right now? So ideally, our algorithm has to return the optimal answer. So we want the best possible answer for it, right? And it should work for all inputs, okay? And it should run in polynomial time for it to be tractable. That's the ideal algorithm. Unfortunately, currently, our algorithms for NP-complete problems can only have 2 out of the 3. So you have to pick which one you have to leave out, okay? So we have 3 ways of coping with NP-completeness, and those 3 ways are result in leaving out one of these factors. So one could be leaving out optimal answer, or leaving out working for all inputs, or leaving out polynomial time. Okay, so we'll discuss 3 ways to cope with NP-completeness, starting with number 1, heuristics. So again, let me show you the list or the checklist of things that we need for the ideal algo. So the ideal algo has to have optimal answer. So optimal works for all inputs and polynomial running time. Okay, so that is the hope for our ideal algorithm. So first, if we use heuristics, okay, you're already familiar with heuristics from your algorithms class, right, in greedy. Okay, so we will use a fast algorithm, so it will still run in polynomial time, and it should work for all inputs, but what we are sacrificing is the optimality. So it doesn't always return the optimal answer. So you remember the greedy algorithms that we had for we had set cover, right? We said that set cover is NP-complete. So it was fast, it ran in polynomial time, it worked for all inputs, but it didn't always return an optimal answer. But it returned an answer that was close to optimal. Okay, so we only had number 2 and number 3, but we don't have optimal. Okay, so that is what we sacrificed. Number two, you could work on special cases. So you could focus on computationally tractable cases, meaning you don't have to worry about all possible inputs. You just need to worry about the inputs that you are most interested in. So you can use a fast algorithm that runs in polynomial time and returns an optimal solution, but doesn't work for all inputs but only for special cases. Okay, so what did we sacrifice here? We sacrificed number 2. It doesn't work for all inputs but only for special cases. So an example of this would be some graph problems have some graph problems that are NP complete could have a polynomial time algorithm if we focused only on trees. Okay, so it will only work all of the time if the graph is a tree. Okay, so if it's a cyclic, it doesn't have cycles, so it's a tree. So some algorithm could run in polynomial time for it. But if you apply it to graphs in general, it will not work because it's specialized for trees. Okay, so that is the second way to cope with NP completeness, which is to focus on special cases. And finally, the third way to cope with NP completeness is to do it in a smart, exhaustive manner. Okay, so you use this when you don't want to compromise the correctness of the solution. So you always want it to be optimal, and you want the solution to work for all inputs. Okay, so what will we sacrifice? We have to sacrifice the third part, which is having a polynomial time. So if you want to return an optimal solution for all inputs, you have to run it in at least exponential time. You will have to wait. Okay, so however, this will be faster than brute force, smart exhaustive. So you can have things like backtracking, which exits right away if it sees that this path that I'm currently taking on will not lead to a solution, so I can backtrack earlier. Okay, I don't have to look at all possible solutions. I could just focus on the ones that are feasible. Okay, so you are being smart. So although you are being exhaustive, meaning you're looking at everything, you are also being smart about it. Like you're not you can give up right away if that solution looks like it will not lead to anything. Okay, so that is smart exhaustive. So it's better than brute force, but it still runs in exponential time. Okay, so that is how you cope with NP completeness. So in summary, for smart exhaustive, you have an optimal answer and it works for all inputs, but you don't have polynomial time. Okay, because it's similar to brute force, only you're doing it better. Okay, for special cases, you have an optimal answer in polynomial time, but it doesn't work for all inputs because you're only focusing on special cases. And then for heuristics, it works for all inputs and it runs in polynomial time, but it doesn't always guarantee an optimal answer, but usually it gives an answer that's close to optimal, just like in greedy algorithms. Okay, so you have to sacrifice one factor in each of the ways to cope with NP completeness. Okay, so why are NP complete problems difficult to solve? Well, it's because the solution search space is very big. So you have way too many possible solutions, and you're looking for that one solution in this very big space. So usually there's an exponential number of solutions, right? So going through it in a brute force manner takes too much time because there's exponential number of them. So the analogy is like you're trying to find a needle in a haystack, okay, or trying to find the ring that's lost in a desert, lost in the sand. So if you lost your ring in the beach or in the desert, then it's probably really difficult to look for it now, right? Or finding a needle in a haystack. So if we had non-determinism, we could guess the choices to make to get the optimal solution without enumerating all possibilities, right? If only we had this non-deterministic computer, if only we had this power of non-determinism, we could guess correctly how to get the answer. without having to guess, going through everything. So can you guess the correct answer without searching? Well, the how do you do it? So if you had the needle in a haystack, what would be guessing, what would be the analogy for guessing the correct answer without searching? So the needle in the haystack would be like using a magnet. Okay, so if there was a haystack and you were looking for a needle, then you could use a magnet to be able to like pull the needle right away without having to go through the whole haystack, right? Or in the ring lost in sand analogy, the solution would be to turn the sand into glass, right? Because you know that glass can be made out of sand, right? If you heat up the sand, it becomes glass. So if you turn sand into glass, if you heat the whole like beach or the whole desert and turn it into one giant glass, then you can immediately find your lost ring, because if everything is in a glass, then you can find it right away. Okay, now what is the programming equivalent of this? What is the programming equivalent of a magnet or turning sand into glass, so that you could look for the answer, or you can find the answer without having to look through everything, without having to search through all possible solutions? Is there a programming equivalent of this? We don't know. Okay, now one of you could be the one of you could prove that P is equal to NP, one of you could prove that P is not equal to NP, and when you do, well, please remember the folks, your classmates and your teacher in ComSci 141 when you win the $1 million prize. Okay, but yeah, who knows what the future holds, right? So anyway, that's it for this video. So we talked about the P versus NP. So polynomial time algorithm exists, then that is the P class. If it's a polynomial time algorithm in non-deterministic computers, that's the NP, the non-deterministic polynomial. We also talked about NP-complete problems, which are the hardest NP problems. So everything can be reduced to this NP-complete. And we can use the NP-complete problems to prove that either P is equal to NP or P is not equal to NP. And then to cope with NP-complete problems, because they are ubiquitous, they are everywhere in the real world, we could either sacrifice the having optimal time by using heuristics. We can sacrifice making it work for all inputs by focusing on special cases, or we can sacrifice running it in polynomial time by doing a smart exhaustive way, which works for all inputs and for that gives you an optimal answer but doesn't run in polynomial time. Okay, so you have to sacrifice at least one to cope with NP completeness. So that's it for ComSci 141. So hopefully you learned something you learned something new, and you could use it, you could apply it in one of your programming applications later on. So hopefully the idea of deterministic finite automata, regular languages and regular expressions, non-determinism, how you can convert finite automata to regular expression and vice versa, and then properties of regular sets. And then we also talked about context-free grammars that you can use in parsing in your programming languages. We talked about parse trees, how to simplify CFGs and convert them to their normal forms, the equivalent push-down automata and how they're equivalent with CFGs. We also talked about the properties of context-free languages, and then the final set, which was the Turing machines and their equivalent languages, which was recursively enumerable languages. We also talked about extensions to Turing machines, but they still define the recursively enumerable languages. And then we also briefly dived into theoretical computer science topics like undecidability, okay, which focused on limits of computation, and intractability, which focused on problems that can be solved in reasonable amount of time versus those that are solvable in theory but takes too long in practice. Okay, and then finally for this last video, we talked about the P versus NP problem, wherein we talked about NP completeness and how to cope with NP completeness. Okay, so I know that ComSci 141 was a very theory-heavy theoretical course, and but I do hope that the theories and concepts that you learned here, some of them could be applied in real world. Okay, and I hope it makes you a better programmer because you have an understanding of how a theoretical computer works. Okay, so what are the limits of computation? This is these are there are some things that a computer cannot solve, and I hope that makes you a better programmer. And if one of you decides to tackle on the P versus NP problem, and if you become successful and you win the $1 million prize, then yeah, just hit us up for a reunion, and maybe you can treat us to a lunch or a meal, right? Anyway, so that's it for ComSci 141. Hopefully you learned some things. If you have any questions, please don't hesitate to ask me. And there is no more next video. This is the last one. So I will see you when I see you. Okay, thank you and have a good day.